Okay, so chapter 4, section 3 is all about specific heat. So specific heat is the amount of energy required to raise the temperature 1 degree for 1 unit mass of a substance. But specific heat can be different for different substances, right? I think that makes sense. The specific heat for water might be different than specific heat for air, than specific heat for nitrogen or CO2. They can also be different for different temperatures. All right, they can be different for different temperatures. For instance, it might take a different amount of energy to raise something from 100 to 101 degrees than that same substance to raise it from 300 to 301. So it might be the specific heat, the amount of energy required to raise it a degree might be different at different temperatures. And it's also different for different processes. The amount of energy needed to raise something 1 degree in a rigid tank might be different from the amount of energy needed to raise something in a piston cylinder device. You could imagine it takes more energy to raise the substance 1 degree in a constant pressure process because kind of remember that boundary work because it takes energy to move the boundary. So we have a constant volume specific heat and a constant pressure specific heat, and they'll be different. They will be different. Okay, the units for specific heat are kilojoules per kilogram K. It's kind of like how much kilojoules it takes per mass and per how many degrees you want to raise the temperature. So in SI units, it's kilojoules per kilogram K. In English units, it might be BTU per pound mass Rankine. BTU per pound mass Rankine. Okay, so if the definition of a specific heat is the energy required to raise it 1 kilogram 1 degree, then we could take that specific heat, maybe the specific heat is the energy per degree T, so take that per degrees T, multiplied on the other side of the equation. We can take that specific heat, and now this might be specific CV, it might be CP, let's put a start out for now. But we take that specific heat times the change in temperature, and we can estimate the change in energy, right? So if we want the change in energy, we can take the specific heat times the change in temperature. Got it? If we want the change in energy, we can take the change in specific heat, or take the specific heat times the change in energy. Now, if this delta E is change in U, then it is CV delta T. Does that kind of make sense, right? CV is kind of a constant volume. For constant volumes, we have U. Whereas the change in energy is delta H for CP delta T. Okay, that right there, and it's boxed in your notes. Delta U equals CV delta T, delta H equals CP delta T. What does that mean? That means if we know the change in temperature and we know the specific heat, then we've got the delta U. Or maybe if we know the change in temperature and we know the CP, we've got the delta H. These equations are true if we assume specific heat is constant over that temperature change. All right, if we assume specific heat is constant over that temperature change. Now, we said that it's different at different temperatures, but maybe it's not that much different. Maybe the delta T is not very large delta T. Then we can just take the CP or CV for that substance, multiply times the temperature change, get delta U or delta H. But more accurately, the CV and CP are not constants. So this right here is assuming constant specific heats. All right, so let's say constant specific heat. But more accurately, it's really like the integral, du is the integral CV dt. The integral dh equals the integral of Cp dt. And so this is more accurate if Cv or Cp are a function of temperature. Function of temperature. All right, here, the main thing. Let's bring it back to the basics. The main thing. Cv leads you to U. Cp leads you to H. Right? Cv leads you to U. Cp leads you to H. So, where can we find these CVs or CPs? Table A2. Table A2. We haven't used this table much yet, so now we're going to use it. So let's look at table A2, and it has three sections, A2A, A2B, A2C. So let's go to our property tables. Property tables. All right, so there's table A1. So now we're going to table A2. This is specific heats of various common gases at 300 degrees. So, nitrogen, you look over here, its Cp is 1.039, its Cv is 0.743, its K, we'll talk about that, it's the ratio of those two. All right, so this is A is at 300 Kelvin. A is at 300 Kelvin, all right? But what if we're not at 300 Kelvin? What if we're not at 300 Kelvin? Well, then we've got table B, which it doesn't have as much, it doesn't have all of these gases, but it does have 6 of them: air, CO2, carbon monoxide, hydrogen, nitrogen. So 6 of those. It goes even further and tells you, hey, at these temperatures, see how it's changing a little bit. So you can go to your temperature. You can go to your temperature and say, okay, well, this one, its CV is 0.788. So if you have one of these 6, then we can be a little bit more accurate at that temperature. If we don't have one of those 6, if we've got butane, then we're just going to have to use those values at 300. Okay, but B, for 6 of those gases, it gives us a lot more temperatures. And then for C, we've got this really kind of complicated equation to get Cp bar, which we will talk about. So let's go back to our notes. All right, so A2A is for several gases at 300 Kelvin. But for these 6 of them, we could go to A2B, and we might have to interpolate. So don't forget, might have to interpolate between temperatures. But also, this is, here we go. We're going to multiply times a change. We are changing temperatures. Should I use T1 or T2, right? This is T2 minus T1. If it's going from 300 to 400, well, should I use the CV value at 300 or the CV value at 400? Use it at the average. So, might have to interpolate. Use the values at T average. Use the values at T average. What if you know T1 but you don't know T2? Then use the value at T1, and the book would tell you, and some people tell you, to get T2 and then interpolate, then redo the problem guessing at T average and redo it until you're kind of doing this iteration. We're not going to have to do that. You can just use the value at T1. Okay, and C are our equations for Cp bar to use for the integral Cp dt. We'll talk about that. Okay, so, for example, if I want a delta U My old method was to finding the U from the property tables, but now my new method is CV T2 minus T1. Or maybe I'm trying to find delta H. My old method was property tables, and my new method is CP T2 minus T1. So use values at A2A at 300 Kelvin, or use values of A to B at T average, or use values of A to B at T1 if you don't know T2. Right? If you don't know T2, then you don't know the T average. Okay. So that was for constant specific heats. These two are constant specific heats. Constant specific heat. Constant specific heat. But C is variable specific heat. C is where we have to do an integral because it's not constant. If it's not constant, we can't just say delta U is C, or delta H is CP delta T. We have to do the integral of C, integral dH equals integral CP dt. Okay, one side note, because this comes up in a lot of these gases, in a lot of these equations. So if we kind of want T1 and T2, so for ideal gases, not liquids, not mixtures, but for ideal gases, we mentioned this before, but P1 V1 T1 equals P2 V2 T2. So in case you know some of these, maybe you can find T2 by this. This is for ideal gases, closed systems. Sometimes if the pressure is constant, then those can cancel out. If the volume is constant, those can cancel out. So just kind of, I don't know, put that in our back pocket. Put that in our back pocket. Okay, let's look at table A, C, A2C. Let's go right here. Property tables. This one right here. This one is complicated, and it is complicated. It's a lot of work for probably not much benefit. Now, this is going to be the most accurate CP value that we can get. You know, these are values at this temperature, but what if we're changing temperatures? This is at 300 Kelvin, but what if we're not at 300 Kelvin? This is the most accurate, and so what this does, this gives us an equation for CP bar. CP bar is the molar specific heat. And so it gives us an equation. So for example, let's find one that we've got for air. Air, the CP bar for air is this 28.11 plus this 0.1967 times 10 to the negative 2 times temperature plus 0.4802 times 10 to the negative 5. These are getting smaller and smaller and smaller. T squared, right? T cubed, all right? And so we could plug this into our equation and integrate this dt as T goes from one temperature to another temperature. And the integral of this would be 28.11 T. The integral of this would be something T squared over 2. The integral of this, something T cubed over 3. And I'd have to plug in my T2 value and subtract my T1 value. It's a lot of math and a lot of work. But it's a little bit more accurate than these constant specific heats. Okay, although this gives us the molar specific heat, let's talk about that. This gives us the molar specific heat. So on this next page, the molar specific heat is the kilojoules per kilomole. See the difference here? Instead of per kilogram, it's per kilomole. And you know that the molar mass is how many kilograms per kilomole. This is in table A1. So the way, and we could look at your units, but the way they are different is Cp bar divided by M would give me Cp. Cp bar divided by M would give me Cp. So I'd get this from the table. I'd divide it by M to get Cp. That's only for that third one, when that long equation, table A2, 3. Also, any other values, sometimes we might look at our molar values, our molar properties. We divide it by moles, the molar mass, to get the specific properties. Okay. Okay, a few things. All right, so remember we said that enthalpy is really internal energy plus the flow work. All right, H is U plus PV. For ideal gases, PV is RT. Let's do a little bit of math here. H is U plus PV, which is U plus RT, right? Just substituting PV as RT. If I kind of take the, it's almost like dividing through by T or dividing through by dt. We can say dH over dt equals du over dt plus R, and this is really Cp right here, Cp. So here we go. Cp is equal to Cv plus R. Cp and Cv are off by a difference of R. And R is the gas constant for that material, for that substance. Cp bar is different from Cv bar by the universal gas constant. So this is the gas constant, table A1. This is the universal gas constant, probably in the footnote of table A1. So why do we have that? Well, maybe you know Cv. In order to get Cp, you just add R to it. But where we really might use it is table A2C will only give a Cp bar, but we can change it to Cv bar by the universal gas constant. Another thing before we wrap up and review, the specific heat ratio is the ratio of Cp over Cv. And sometimes these can be it's very interesting that these are the same for some gases. It's 1.667 for monatomic gases. K is 1.4 for air. And it's practically constant at any temperature. So again, you know, if you know Cp and K, you could get Cv, you know, a few different ways. But here, last page, summary. This is the big deal. If you didn't listen to all that, I hope you're still watching this video. This is it. Now we're going to do the same equations, but now we have two more ways to calculate delta U. Our old way was from the property tables, right? From property tables, okay? And we're going to say that this is the most accurate, but it takes a lot of time. What might be quicker is to do Cv delta T from table A to A or A to B. All right, table A2A or A2B. This is the least accurate. To get a little bit better would be to go to table A2C get Cp bar, then change it to Cv bar, change Cv bar to Cv, and then integrate that long equation that had a constant and then something t squared, something t cubed, integrate that, and so then something t squared over 2, something t cubed over 3, something t to the 4th over 4, plug in t final minus plug in t initial. A lot of math to get it middle accuracy, a little bit more accurate than the constant specific heats. All right, that's for finding delta U. What if we want to find delta H? Then our old way from property tables. Our newer way from table A to A or A to B. And remember, for these, use the value at T average and interpolate if you need to. And this, from table A to C, we would get Cp bar, integrate it, be careful though, divide it by the molar mass to get Cv. And a few things to remember. The specific heat ratio is Cp over Cv, or Cp is Cv plus R. And remember that Cp, the specific heat, is different from the molar by the molar mass. All right, so that equation right there. So you'll see that the second method is going to be a really probably quicker and easier method to give us a decently accurate delta U or a decently accurate delta H using constant specific heat. So when I say constant specific heats, I'm talking about number 2. When I say variable specific heats, I'm talking about number 3. And when we say property tables, I'm talking about method number 1. All right. Let's do some problems.